Okay, so today's lesson is going to be on inter and intramolecular forces. And now this concept can be a bit tricky sometimes to students because the words seem so similar. So let's start with looking at the difference between an inter and an intramolecular force. An intermolecular force is a force that is between the particles. For example, if I have glucose, all right, and you've talked about glucose in biology, and we learned a lot about glucose. Two glucose molecules have an attraction to each other. All right, that is the intermolecular force. If I was to draw glucose, and here's the actual chemical structure of glucose, so you can see it's a bit large and tricky looking. The intramolecular force is the force right here, these covalent bonds that are holding together the elements within the compound. All right, so a force of attraction between two glucose molecules themselves is the inter. The intra is that force holding those elements together. So let's look at the different types of intermolecular forces. And we're going to list these from strongest to weakest. So our first type of intermolecular force is a network covalent solid. This is going to be compounds containing silicone, diamonds, quartz, which I spelled diamond wrong. All right, quartz and graphite. The next type is going to be an ionic and a metallic bond. All right, so we're going to say that ionic and metallic bonds are of equal strength unless provided additional information in order for us to know which one may be a little stronger or a little weaker. But at the purpose of this course, I'd have to give you additional information for you to determine that. Otherwise, they are equal. We have hydrogen bonds. A hydrogen bond really tricks students up as well. All right, a hydrogen bond is a force of attraction when a compound has a hydrogen combined to a nitrogen, a hydrogen combined to an oxygen, or a hydrogen with a fluorine. So when we look at water, for example, I have two particles of water here, H2O, H2O. Now remember, water is polar, so the oxygen has a partial negative and the hydrogen has a partial positive. So the partial negative of the oxygen is attracted to the partial positive of the hydrogen. This attraction between the partial positive of the hydrogen and the partial negative of the oxygen, that is the hydrogen bond, which is an intermolecular force. The covalent bond holding the hydrogen to the oxygen is an intramolecular force. All right, so when we talk about a hydrogen bond, the hydrogen bond is actually occurring between two different species. Let me rephrase. It's occurring between two species, but it may not be different because in this case, these are both water. So the hydrogen bond is not the hydrogen that is bound to the oxygen. That is an intramolecular force. The hydrogen bond is the attraction between the hydrogen of one substance and the oxygen of another. We have dipole-dipole. This is any polar molecule. For example, if we were to look at hydrochloric acid, again, hydrochloric acid is polar, so we have a partial negative on the chlorine and a partial positive on the hydrogen due to electronegativity differences. And the dipole-dipole here is the attraction between the dipole of the chlorine and the dipole of the hydrogen, that partial negative and that partial positive. Our final phenotype is going to be a London dispersion force. All right, sometimes we abbreviate that LDF. Now, here's the thing. All substances will have London dispersion forces to some degree. Nonpolar molecules have only London dispersion forces. So it is possible for a compound to have more than one type of intermolecular force. Nonpolar compounds will have only London dispersion. Now, the strength of the London dispersion usually will increase as the molar mass of the compound increases because those compounds tend to have more electrons. All right, so the more electrons we have, the more what we call polarizable the substance is. All right, so the more polarizable, so if we think about this, electrons are constantly moving. All right, and it's possible that the electrons may be in the same location at the same time for a brief moment in time. So the more electrons we have, the more likely there are to be a bunch of electrons at the same spot at the same time. And let's think about this in terms of us walking through the hallway of our school. If just our class went through the school, down the hall through the school, and I was to tell you guys, go walk around the school. And then I was to give everybody a walkie-talkie, all right? And I said, and stop. With just our class, the likelihood of you being clumped together in one area of the school is pretty small. You guys would be able to spread out pretty easily. Now let's think about the entire school. All right, you guys are electrons, so now the entire school during class change. All of the students are going down the hall at the same time. So that hall is very crowded with students. All right, it's crowded with electrons. So if we were to stop students at any given moment in time, when all the students are during class changes, we're going to find there's a high probability there's a bunch of students in one area at one time. And that's what we mean by polarizability. So if we were to look at water, for example, water, if we were to draw water and we were to look at it, we see it will have London dispersion forces because our hydrogen and our oxygens do have electrons. Those electrons are moving. So there is some polarizability there. It is a polar substance, so it has dipole-dipole forces, but it also has this covalent bond between the hydrogen and the oxygen, which is able to give it hydrogen bonding as well between another water molecule or something else that has hydrogen bonding abilities as well. All right, now, water has three different intermolecular forces. The hydrogen bond is the strongest of the three forces. The London dispersion is the weakest. So when we talk about the strength of the intermolecular force of water, the hydrogen bond is going to be the main player there. That's the one that's going to really be determining the majority of that strength. One last thing I'd like to come back up here and add is a network covalent solid. A network covalent solid is simply just a repeating pattern of a solid. All right, so if I was to draw a substance, and let's just say it had a square structure, all right, just for simplicity purposes, we would have this repeating pattern over and over again. These are covalent bonds, but because the pattern repeats, that is what a network covalent solid is. Now, intermolecular forces are ultimately going to depend on the Lewis structure. So we're going to have to be able to draw Lewis structures. If you don't remember how to draw Lewis structures, or you are new to this video and you've not learned that, then you'll need to go watch my video on how to draw Lewis structures. All right, BF3. When we look at our periodic table, we find that BF3 has 24 valence electrons. And again, if you're not sure where I got that from, you're going to want to go to our video on valence electrons. When I draw out my BF3, I find the molecular structure to look like this. All right, and we call that the Lewis structure. All right. So when I look at this structure, now remember boron is in group 3A, so it only needs 6 electrons. This is an example of an incomplete octet where boron is stable and happy. All right, so based upon my structure here, it is trigonal planar. I'm going to find that this is a nonpolar substance. And because this molecule itself is nonpolar, it's trigonal planar, and all 3 parts are of the same electronegativity values, then it's nonpolar. So the only intermolecular force that we have here is a London dispersion. All right, NCl3 has 26 valence electrons. So when I draw NCl3, I find that it has, and I'm going to use dots here because sometimes the line that I drew up here to simplify gets a little tricky when you have chlorine. It looks sort of like a line and the L, so we'll just use dots here. Now, when I look at this substance, all right, I know this structure is a bent structure. This lone pair is pushing these chlorines down and out of an angle to where the dipoles are not able to cancel. So it is a polar substance, so it will have a dipole. Now, all substances do have London dispersion to some degree because each one of these, again, has electrons. All right, nitrogen and the chlorines all have electrons. But the strongest of those forces would be the dipole. All right, let's check out Br2. Br2 has 14 total valence electrons. So when I draw Br2, I find it to look something like this. And this is going to be an overall non-polar substance. So the only force of attraction we have is the LDF. All right, HF has 10 valence electrons. And when I draw hydrofluoric acid, my Lewis structure looks like this. Now we know it will have LDF, London dispersion forces. It is a polar substance, so it will have a dipole-dipole force. But it does have a hydrogen covalently bonded to a fluorine, so it has the ability to hydrogen bond with other substances. So of these 3, the hydrogen bond is going to be the strongest. All right, and finally, SiO2. This has silicone in it. All right, so silicone is going to create a substance that has a, let me spell that correctly, network covalent solid. And of course, it does also have LDFs as well, but the network covalent solid is going to be the strongest of that. All right, network covalent solid are our strongest of our types of intermolecular forces. So number 6 asks us to rank these in order of increasing boiling point. This is going to be based upon the temperature, or the intermolecular force. The temperature at which something boils, now when we go, is our boiling point. Now what does that mean? We're going from a liquid to a gas. So when I go from a liquid where particles are closer together to a gas, we are breaking all of those intermolecular forces to allow our gas particles to be furthest apart. So the amount of energy needed to break those intermolecular forces is based upon the strength of the intermolecular force that substance has. The stronger the substance intermolecular force, the more energy is required to break, and therefore the higher the boiling point. So when I look here, if we are increasing boiling point, we are going from smallest to largest. All right, so my largest is going to be my silicon dioxide. So I'm just going to go ahead and put that down here at the very back. That is the largest. Now we are going to use greater than or less than signs. We are not going to number or create some random key that makes no sense. We are going to write greater than and less than signs. So silicon dioxide is greater than this, all right? And this would be smaller than the silicon dioxide. Now, when I come back and I look, I have two substances that have only London dispersion, which are the weakest. So which one of these is weaker? And that we're going to look at molar mass, all right? And at the level of this class, we're going to stop right there. There are exceptions to this, but we're not going to go into those exceptions. We're going to just stick to the basics and look at only molar mass. So when we look at these two substances, and we were to pull out our calculators and calculate the molar mass, we will find that the molar mass of BF3, and I'm just going to do MM for molar mass, that gives us a value of 67.81, and the molar mass of bromine is 159.8, and of course our units there are grams per mole. Now in this video I'm making a lot of assumptions here that you have previous information. If you are unsure of how to determine molar mass, you need to go watch my video on molar mass. 67 is a smaller molar mass than 159, so BF3 is going to be ranked as the smallest. BF3 is smaller than bromine. All right, now we've got 3 of our 5. When we come in here and we look, dipole-dipole is a weaker intermolecular force than the hydrogen bonding. So NCl3 will go next. And then the final one will be my HF. All right, and let's just go ahead and fill in my SiO2 here just to make it a little neater. All right, so in order of increasing from smallest to largest, we start with our boron trifluoride and we end with our silicon dioxide.